Okay, let's get started, please. So, welcome to the last talk of this morning, and speaker is Chris Lustri, and he wins a prize for the best title of. And so, Chris, all yours.
Thanks very much, Gerald. Hi, everyone. So, for those of you who don't know how the globe works, there's a lot of mathematicians here who aren't physicists, so I should probably explain. Right now, it's summer in Australia. I got some photos from my family yesterday. They were at the beach. I am not. I've spent the last 3.5, 4 months at the Newton Institute in the ARA program that we're all here for. And I had some quite lofty goals, some things I wanted to understand when I came here, which is why I voluntarily left the first good summer in several years. And the big question, I suppose the overarching question I want to answer here was it worth me doing that? And in seriousness, what I actually want to talk about is some of the problems that I did while I was here, and why I did them, and what I hope to get out of them, and what I think they will lead on to. None of these problems are finished. These are all problems which were either started or largely done during this program. Obviously, all of these problems have collaborators. That was the whole point of being here. They all look at things that I've been interested in or thinking about or wanting to know about for some time. Transasymptotics, looking at discretization. I wanted to understand the Borel plane a little better, and in particular, sort of pulling out nonlinearity. And I wanted to think about analytic continuation and how we can use that even when perhaps leading order solutions aren't so nice. So each of these problems, I'm going to just tackle one at a time. There's sort of notionally a through line, but not really. I'm hoping each one takes about 10 minutes and I can get you out of here early. But I haven't timed this out, so we'll see how it goes. So the first problem, transasymptotics for Berger's equation. In particular, understanding the poles that form in early time Berger's equation. This was done largely with Scott and Inyesh. Berger's equation. Viscous Berger's equation, so you've got ut plus ux, so it's basically the simplest nonlinear thing you can put together with this mu uxx. And we're going to start it with an initial condition. Scott McCue introduced this problem to me and sort of said, hey, there's some interesting corners to tackle here. And I'm going to talk a little bit about what was sort of shown. Now, this is a nice nonlinear PDE. It has an exact solution. It's kind of hard to evaluate sometimes. These integrals could be highly oscillatory. We wanted to understand the effect and development of singularities in the complex plane of the solution, but we wanted to do it in a way that can be applied more generally. The fact that this has a solution is nice, but most nonlinear PDE don't. Well, not one you can write down in closed analytic form, obviously. So I have here a couple of values of this, this viscosity and the complex plane. So we've complexified x, so y being 0 is real. And you can see there's these singular points, and you can tell these by the color wheel points. There's these poles and zeros that form in these lovely lattices. It's an interesting question to ask where they come from, because they certainly weren't there in the initial condition. The initial condition had a simple pole at I and a simple pole at minus I. But now there's these whole strings of singularities which we want to understand from whence they appear. Some very nice pictures. These were prepared by a student, Daniel van Heuvel. He's very good. I did not make them. So when you want to know what's happening at small time, you start by doing a small time expansion. Just writing a power series in T, seeing what happens, and you can calculate the first few terms. And they're very nice, and they are all singular at I and minus I. And they don't give you strings of poles. This is not wholly a surprise. We expected to see this. You need to do a bit of a rescaling. Scott McCue identified this rescaling to look near the pole at small time. So the new rescaled variable is this xi here. So you're looking near the pole at small time. And you get a new PDE, not appreciably nicer, but maybe we can do something with it. Well, we're going to do a small time expansion with it. of our inner PDE. So we do this small time expansion, we get a leading order equation, it's second order, but we can apply a boundary condition and get this. Scott McCue talked about this in a lot more detail in the second workshop. I don't want to retread that ground too much, but please, if this interests you, go and watch his talk. It was really informative about what all of this means and where it comes from. Now, it turns out this has an exact solution in terms of special functions. I'm going to write it down, and then we are going to pretend it does not exist. Because again, we want to come up with a more general method that we can use for nastier PDEs than, say, Berger's equation. But it is very nice, and it was very good for validating our answers, because we could just look at where it predicted the poles would be. Where it predicted the poles will be is the white dots. Bang on. And that makes sense. We haven't really done anything unusual yet. The solution has strings of poles and zeros that match up with the numerics. And because we were in this scaled inner region, we now have a picture of what is happening. The singularities are rushing out of the point I in the very early time regime. They're shooting out in this great big rush to produce these lattices. It's very nice, and we'd love to see it, but we'd like to be able to see it without having to rely on these special functions. So what I'm going to do, when I came here, I did not really know how to use transasymptotics. Now, thanks to Anesh's talk and also work we did together on this, I have a much better idea, so hopefully I won't mangle it too badly. We want to study the solution to this equation. You can use WKB to get both the algebraic leading order and also the exponential that we expect to cause us all the problems. We can find the Stokes structure, which I think I'm not going to go into detail here. I think you can use your favorite method, matched asymptotic expansions, Borel plane, hyperdeterminants, something else. But you can certainly compute the constant. Now, we know it's algebraic in this direction. That's the initial condition. That bit we know. There's no exponentials present here. If there were, they would be large, so they aren't, which means this anti-Stokes curve does nothing, except now we get into this bit, this sector, and if there were any exponentials, they would be small. There aren't, but there will be soon, because we cross the Stokes line. You cross the Stokes line and the small exponentials appear, something that I hope many of us have seen before. Then you get to the anti-Stokes line, and in the past, this is normally where I've stopped. But this is where the poles will form, because generally, a string of poles will accumulate along an anti-Stokes curve. That's where the nonlinear effects make things grow. So what we want is to track that small exponential and see what happens when it's not small anymore. So we can compute the Stokes constant. You don't really need to know what it is for the purposes of this talk, but it's helpful to know that it's 0 below the Stokes line and not 0 above, and smoothly varies between the two in a narrow region, but we don't really care about that for this problem. So I do a quick coordinate transform just to make f nice. So my independent variable is now leading order 1, and that x just makes our WKB a little bit easier because that's the exponent. So we get this new ODE, which is the thing we'll actually do work on, and we find a nice general form for the subdominant exponentials. So each one has this multiplier of x and this e to the minus x, e to the minus 2x, e to the minus 3x. This is our transseries. And with a nice little dominant balance argument, you can find the power of those x's being this 1 minus n, a half plus I over 4 mu. I've never seen one before with the complex power. It's really quite nice that it falls out that way. So we define a new exponential variable, the transseries variable, and this is the magic trick. Well, no, the magic trick's on the next slide. So C is the Stokes constant. When the Stokes constant is 0, there's no exponentials, nothing is going to happen. So as far as the rest of the analysis is concerned, we live in the region where C is non-zero. That x will be taken to an increasing power at each order, and the e to the minus x comes from this one here. And we assemble this in a transseries, and with a bit of sort of jiggery-pokery, combining it, we get this thing here, this double sum. A sum in x powers of x as x goes large, and a sum in powers of tau. And in the region where the exponential is small, at least, this is fine, because tau is exponentially small. We also know from the boundary conditions in the Stokes switching that we have these two constants. They're there to close the system. They will be important. They caused us a little bit of strife, but we got there in the end. You can find as many terms as you want in this double sum. Just keep turning the handle, and the terms will fall out. Just keep doing matching. It won't tell you where the poles are, not yet. Currently, this is only valid where tau is small. So this is the transseries step. The next bit is the transasymptotic step, and this is the bit that I did not know how to do properly before I got here, which is essentially resumming in a way that, frankly, you have no business being allowed to do. Transasymptotic summation is saying, well, we have L equals 0, M equals 0 of these two power series. We're going to flip the order. This is very divergent, but we're okay. This will work. So we flip the order and pull out the x, so we still have a power series in x. We're still thinking large x, but we're saying, tau can be anything at once. And we're actually going to resum this to get this series in M. So now we have a power series in x, which can vary freely in tau. And tau can, in fact, grow. And as long as AM doesn't get too nasty, and sometimes apparently even when it does, but in this case it happens to be kind of well-behaved, this will work. This slide took me a very long time to understand, but this switching is the magic trick that lets you extend your small exponentials to understand what's going on as they grow, to learn where the poles are, to do all of these things that we kind of knew you could do, but maybe we didn't track all the way through. It's an incredibly powerful technique. Because you can then take this and put this back into your ODE, and you do another game of matching, and you get a nice nonlinear ODE for A0. And A0 spits out something that, in this case, is nice and rational. Won't always be this nice, but it's a relatively straightforward example, so that's nice. And the best thing is A1, A2, A3, they're all linear, so they're not going to introduce any new poles. This is going to tell you where your poles are, more or less, because this is rational. Where this thing is a pole, and this is in tau coordinates, that will be where the poles in our original function are. So the final step is to go back to the original coordinate system. We posed our problem in x. We want to know where the poles are in x. We have to invert this. So we have poles, and you'll see they are at tau equals I over 8 mu, so not mu. Pretend there's an I over 8 there. Mu I over 8 equals this thing on the right. And then you can invert that. You can invert that exactly. You can invert that on a computer quite nicely. You can invert that as a fixed point iteration scheme. And if you take logs, you can actually see where the string of poles comes from. It comes from this 2n pi I. So you can do this, and you can actually fish out all of the different logs. Now, this gives you the leading order of where the poles are as x becomes large. But if you take more corrections, more an, you can actually adjust that and get arbitrarily better approximations. So not only can we recover the asymptotics of the special function that's known, we can push them as far as we like and get incredibly accurate pictures of where these poles are. We haven't sort of dotted all the I's and crossed all the T's, but this is a really nice example of how this simple sum reordering technique can be used to locate poles in the complex plane. Ines has used it for various Painleve equations. It's an incredibly powerful technique. This won't be the last time you see it in this talk. However, this is all I'm going to say about Berger's equation. So that was problem number 1, me learning how transseries worked. It's really nice. We're gonna write this up. So the next thing I wanted to do was study a discretized KdV equation. This is essentially just a great big jump from the previous talk, but one of the other things that I've always been very interested in is discretization. What is the actual effect of discretization itself? And that's because you can think of discretization as a singular perturbation. And singular perturbations can induce oscillations and Stokes phenomenon, and maybe we can pick these out. Now, this is based on some work I did a few years ago, at least initially with Nalini Joshi, where we realized that discretizing KdV can induce some interesting behavior. So the KdV equation, for those who are not familiar with it, is this nonlinear equation up here. It's actually not wholly dissimilar to the viscous Berger's equation that we just saw, except instead of viscosity, you have dispersion, so a third order derivative. This equation is well known to generate nonlinear dispersive waves. I didn't make these pictures, I cribbed them from this paper. You can see they've got a sort of peak and then a much wider trough. These are nonlinear waves. They are not a sine wave, which is sort of relevant. And I wanted to know, okay, if I've got waves in a KdV equation, hopefully I should be able to see these nonlinear effects. So I discussed this with Sam Crew, and we came up with a way forward. So what I wanted to do was study a discretized KdV equation. So instead of that third derivative and the second derivatives, I've just replaced them with their finite difference equivalent. This is not the discrete KdV equation. This is definitely not integrable. This is the dumbest possible discretization you can come up with, but it comes up with interesting answers. So we've got this advanced delay equation, and you can actually replace the advances and delays with infinite order Taylor series. So I'm just expanding around h is equal to 0. So you can see, for instance, this is the u of x plus 2h has this expansion here. I wanted the discretization in x and t to scale the same way, but they didn't have to be exact, so the sigma is just the ratio of those discretizations. But you get this, and this is singularly perturbed. It's infinite order. Now, you might think that's a problem, but actually there's a paper from a while ago by King and Chapman where they show how you can use matched asymptotic expansion type exponential asymptotic approaches to pull out the small exponentials. It's really nice, and I used a lot of those techniques here. So it's a singularly perturbed PDE. It has Stokes switching, and it turns out, and this is the work I did with Nalini, we were able to pull out what the exponential asymptotic waves were. And KdV likes to have symmetric waves. That tends to be the stable wave structure. So on this side, you've got the R minus, which is this thing with the minus sign. On this side, you've got the R plus, which is this thing with the plus sign. And the exponential asymptotics, at least as I understood them at the time, gave out this sine wave. Now, I was only looking for the leading order because I wasn't so much interested in the form of the waves as showing that the act of discretization itself was sufficient to induce these waves. But the more I thought about it, the more sort of KdV as a nonlinear wave equation kind of never left my mind. I wanted to understand the nonlinearity in these waves. This method isn't going to do that. This method, as I was able to do it at the time, was only ever going to give me the sine wave, a nice prediction of the period, the amplitude, but not the nonlinear corrections. To get the nonlinear corrections, I needed to get the further exponentials, the other bits in the Borel plane for people who think that way. And in fact, that's exactly how Sam thinks. So we were able to sort of come up with a plan of attack. Before we tackled the full problem, though, we started with a toy problem just to validate that it would work. And we put this one together. So it's still an advanced delay equation. It's much simpler. And we wanted to come up with the formal power series in the large X limit, and then apply Borel plane machinery to it. So we took the Borel transform, and we took a part A approximate of this result. So by getting lots of terms in the power series, we could generate a part A approximation, and that would tell us where the nice simple poles in the Borel plane were. And they are regularly spaced. They are at pi I, 3 pi I, 5 pi I. So exactly the same place as we saw here. And it turns out this is incredibly generic behavior. You see this all the time. So maybe everything's nice and easy. Maybe this generic behavior has everything we need to know. Because once you've got poles in the Borel plane, you can work out the Stokes coefficients just by integrating around the pole. You integrate around the pole, and what falls out is the Stokes multiplier. So that's very nice. So then we decided, well, the easy problem was easy. I wonder if the hard problem will be easy. No, but it'll be interesting. You still get the pi I pole, and you'll in fact still get the pole at 3 pi I and 5 pi I and so on, but you get all of this other stuff going on. Now, when you do a part A approximation, and I will talk more about this later, it can only find poles. So if it sees a branch, it just goes, well, that's a whole lot of poles lined up. So these accumulation of poles is actually a branch in the Borel plane. It's a logarithmic branch, we were eventually able to figure out, but it's hiding because the logarithmic branch point is sitting right on top of the pole, which means you do the pole, you don't see the branch unless you're looking for it, but it makes calculating the Stokes constants a pain because we can't just integrate around it anymore. We have to be a bit smarter. Well, we have to be a bit smarter. Fortunately, Gerald and Ovidiu Costin were already a bit smarter, so they came up with sort of some really powerful techniques which we then utilized, or started utilizing. So they looked at uniformizing maps. This is one of 3 references, but it's the one that I think was the sort of the first one, which allow you to apply a conformal map and split off the pole. So this map is the first one of this. There's some noise which we have to deal with and haven't dealt with yet, but you can see there's a pole sitting on its own and at I and minus I. That is the pole that was sitting at plus or minus pi I. So we were able to split them off when the logarithmic branch stuff is somewhere else. The pole is isolated, we can find the Stokes constant. What we can then do is isolate and remove that singularity, repeat the process to get the next one, integrate around, get the Stokes constant, isolate, remove, find the next pole, and so on, and hopefully then at least find the leading order behavior at each exponential order, and thus identify the nonlinear behavior. Because what we'd love to see is sort of a small version of those waves we saw in the gradient catastrophe. I don't know if we will. We haven't finished this. We got as far as this. We were like, yep, that's probably doable. So we moved on from there. But this actually opened a whole lot of questions. Not just what do the waves look like, which hopefully we should be able to get from here. Will we see the typical KDV behavior? You have to think so, but I don't know yet. So we'll see how that shakes out. It got me thinking about other equations we could do in much the same way. For instance, integral equations, you could discretize Benjamin-Ono, write down the Riemann sum. I haven't discretized the derivatives, but you could do that. This is not a good way to think about the exact singular integral, but it's an interesting discretized equation to look at. So I want to do that because Benjamin-Ono plays in the back of my mind rent-free. But it's something that I wanted to sort out. Another question that came up, because Sam's done a lot of work on parametric resurgence, looking at the Borel plane when you have these small parameters, which he talked about in his workshop talk in the second workshop, and I thoroughly recommend you looking at, and Phil touched on it yesterday as well. What about this sort of very canonical nonlinear PD example that I think everyone who's played in these games for a number of times has tried their hand at? Can we see the nonlinear waves arising in this 5th order version? So this is shallow water waves with surface tension. And you might think, well, there's only one singularly perturbed term there, so that's probably easier. It's actually slightly tricky. There's something slightly non-canonical about it, and in fact, any version where it's just a singular perturbation is that to understand those in the Borel plane, you have to do the asymptotic matching that Sam and Phil mentioned. There's this boundary layer around the singularity in the Borel plane that you need to match to understand. But that raises a really important question because that is definitely not present in the discrete problem. Where does it go? In the discrete problem, you can use the boundary layer theory, but it's a fake boundary layer. The thing that it's tending to is just what you find when you do the boundary layer. So there's not a real boundary layer there. How is it that the much, much, much more singularly perturbed problem is actually, in some sense, much, much simpler to do? We haven't quite got to the answer, but that is a question that's worth thinking about. This is essentially the equation you get when you truncate these sums after one term. What happens if we truncate it after 2 terms, after 3 terms, after 4 terms? Seems like that's something worth thinking about. But this is probably too hard a problem to really get a handle on what's happening if we do these truncations. Maybe we should do an easier problem. So, problem number 3. I've been thinking a lot about how this discretization can get incredibly nasty, but then as the sum goes off to infinity, become incredibly nice. And a problem that I've been working on with John King, and we've sort of all done bar the shouting, is what happens if I have some family, and what I do is I just keep letting that truncation order grow or become smaller depending on which end you want to come from. So maybe a discrete problem that's very, very nice. The first discrete Painleve I equation is very, very nice sometimes. It doesn't have chaotic behavior at least, so that's a good start. We want to study a discrete problem, but I want to use the same methodology that I used in the previous example. So I want to take those differences and I want to rewrite them as an infinite sum. Now I do a bunch of scaling, pick some constants that are nice, and I end up getting this infinite ordinary differential equation down here. At leading order, in H, as H becomes small, you get this. This is a scaled version of Painleve I. And that's very nice because Painleve I has some incredibly well-behaved solutions. So we're going to pick everybody's favorite and make that our leading order solution. So what I'm going to say is Y0 is the tree truncate solution to Painleve I, scaled a bit. So the far field behavior is 2x over 3 square root. We won't use that. That's just there so the many, many experts in Painleve I here know exactly what I'm talking about immediately, as if you didn't already. These are poles. It is a singularly perturbed problem. We expect them all to generate Stokes lines, and that is a lot of Stokes lines. But we can deal with that as long as we understand what's going on. So for now, I'm just going to tackle the discrete problem in much the same way I did the discretized KDV. Posit some late order terms, find the singulant. Hey, look, the Borel plane is going to be odd versions of n pi I, exactly what we found in the previous question. Should not come as a surprise. That is very generic. There should be a tilde there that I never fixed. So the prefactor, y, goes as this two-parameter problem. I've written down the first gamma. The second gamma was 0. I forgot to write that down, and John ticked me off and told me to fix it yesterday. I did not. But there are two different contributions, one associated with each individual prefactor expression. Now, I'm not going to dive into it here, but most people who've done these, you often find that the prefactor only has one parameter at leading order. These two-parameter problems came as a bit of a surprise to me, but then it turned out that's actually something that Chapman and King encountered in their early work. So it's a little bit more tricky to deal with, but you end up getting the nice standard error function smoothing on the Stokes line. So even though it's a little bit different to what you see in continuous problems, it does the same thing. And the Stokes phenomenon in the discrete problem is pretty well behaved. So we posed our initial condition on the positive real axis. So there's this first pole, and we know that the exponentials have to be off, because if they weren't off, it would be an anti-Stokes line, and they would be growing, so they're not. You can then continue up, but as soon as you get to the anti-Stokes line generated by the next two poles, generically you're going to run into larger exponentials that you weren't keeping track of if you just look at the leading order solution. So your leading order approximation is no longer a good description of the problem. That's fine. This all seems very sensible. Horizontal Stokes lines, everything is 90 degrees. There's Stokes switching extending vertically from each pole. There's anti-Stokes lines extending horizontally from each pole. This is an integrable problem. And what we're going to assume integrability means for the purpose of this talk is the only movable poles are the only movable singularities are poles, which is to say we expect when we cross this anti-Stokes line, not unlike the first problem I did, that a bunch of poles will accumulate along that curve, because integrability is incredibly nice. It's too nice, and I want to understand the not nice part of this. So what I'm going to say is, what if I truncate this at a number that is not infinity? Now, if I truncate this at k equals 1, I just pick up Painleve I, so it's integrable. If I let this thing go to infinity, I pick up discrete Painleve I, which is integrable. So both ends of this family are integrable, but in the middle, all bets are off. And what I wanted to see is what kind of nonsense appears and where does it go? None of the intermediate equations are integrable. Generically, we expect branch points. That's kind of what you expect in nonlinear ODEs. Just branch points, certainly no other interesting behavior. No, we'll find something very cool. How am I going to do that? Well, I'm going to look in the Borel plane first. I didn't compute the Borel plane. What I really plotted was chi-dashed. Because the singulant is linear, this is equivalent to the Borel plane, except I'm just only looking at where the singularities are. So I'm saying I'm plotting chi-dashed. This is the same information the Borel plane can give you, but I didn't do the Borel computation, so I don't want to say I'm plotting the Borel plane here, even though it's functionally the same thing. So if I look at k equals 2, the first singularly perturbed member of the family, I have poles at plus or minus 2 root 3i. Nice, on the imaginary axis, all very well behaved. If I look as k goes to infinity, which we've thought about before, we get our odd multiples of pi I. All on the imaginary axis, all very well behaved. So maybe nothing interesting happens. But as soon as you go further, you start to see this structure emerging. On the one on the left, so that's k equals 3, so this is a sixth order equation. You've got 4, as well as a double pole at 0, which I didn't bother drawing in. So you've got these 4, and they're not on the imaginary axis anymore. And when I go up to the 8th order equation, you've got 6 non-zero chi-dashed, and none of them are on, well, 2 of them are on the imaginary axis. But it's getting a lot more sort of exciting. Exciting is bad, because exciting means whatever I thought I understood was going on is not going on. So what I did is then I turned it up to a lot more. And actually, as I explored this, it became apparent what was going on. So this is k equals 100. And you'll see poles are starting to line up on the imaginary axis. And those ones on the imaginary axis will actually tend, as k goes to infinity, to plus or minus odd pi I. But you get this sort of rainbow at the top and the bottom. And the more you take, the further away it goes. In the limit that k goes to infinity, this is super singularly perturbed. Those ones that disappear off to infinity will vanish. The poles assemble on the imaginary axis, but the non-imaginary ones will get bigger and bigger and bigger, so the exponentials will actually end up becoming less and less important until in the limit that k goes to infinity, you'll get those poles up and down the axis. So I was a bit worried that these kind of unexpected ones were turning up. This didn't match my intuition for what discrete equations should do. But this made sense of how you could recover the well-behaved problem in the infinite limit. So the one last thing I wanted to sort out was, can I see these branch points or whatever sort of weirdness is appearing in these solutions? And to do that, I returned to the transseries approach, because that will let me tackle singular points. It's actually slightly easier to do transseries in this problem than the first one. And this you'll see again and again. If you do transseries and let the independent variable become large, then you get quite nasty expressions for your transseries parameter. To invert it, you need a bit of Lambert W function or fixed point iteration. But if it's just a small parameter that is constant, then your transseries is just kind of the scaled exponential. So I do the same thing as before, and that is to say I'm not going to go into the details here, but you write out the double sum, and then you do the resummation, and you can get equations for the leading order behavior of each exponential like I did before. So for k equals 2, as tau becomes large, our equation looks like this. So I wasn't really sure what to do with that ODE. I talked around, that thing equals 0. So I talked around to a few people. John King took one look and said that has natural boundaries in it, and he was right, which is infuriating. But I didn't know that at the time. So I said, how do I find poles? Well, I've become a bit of a dab hand with this Pade approximation thing, and it's pretty easy to turn that into a power series around 0. It's quite nice, so let's do that. So I did it for k. So what do I mean by that? Because I've sort of referred to Pade approximation, but now it's time to talk about what we're doing. We are writing it as a rational function. As I've mentioned, it will only see poles, but the way poles accumulate can tell us what's actually sitting under there. Whatever I find this way, I'm going to want to validate with numerics, which is one of the odds and ends I still have to tidy up. But I'm hoping to see accumulations of singularities that tell me that there's branch cuts. So I do k equals 2, and I get something that looks very pretty. What that is, currently conjecture, but this is what it is. We'll do some numerics. You've got branch points all accumulating on this natural boundary. The more we take, the more we'll see. There's nothing that will get us past that. There's some noise that I didn't sort of clean up. These aren't real poles. Those are just noise. They disappear if you take other orders. You can clean those up by taking more digits. What you actually see is this beautiful fractally natural boundary. And this natural boundary is in tau, don't forget. So for tau being order 1, tells us that it's in an area where that exponential has started to grow. So this is on the big side of the anti-Stokes curve. You're eventually going to run into this natural boundary. Inverting this gives you a log, so you're going to sort of see this kind of series of natural boundaries assembling themselves in a nice way. Continue that up to K3, gets even nicer. Still, it's starting to look a little more regular. It's still an assemblage of branch points. There's still noise I haven't cleaned up. But you can see it's still kind of an order 1 distance away. We're still living in the region where the exponential is growing, but we're running into this natural boundary. Nothing wrong with that. It was a surprise to me. I've never really thought a great deal about natural boundaries, but it works quite well. So as you keep going, so here I drew up k equals 30. It seems like it's tending to a relatively circular shape, which is quite nice because then I can just convert back, get something that's going on in x. I convert back. XP is the pole location. M is the number that indexes, M is a number that indexes the exponential, but really we only need the first one because you can't continue past it. This is going to be an order 1 type thing because the intersection point is a nice order 1 behavior. It's not going to 0, it's not going to infinity, it's probably just balancing out. So really this is the term we care about. This is going to tell us where the branch point goes. H is small, so this is going to be positive. If we fix h and keep increasing k, our branch point is going to move further and further away. It's going to disappear eventually as k increases. Just like the poles in the Borel plane disappeared off to infinity, the branch point will shoot off to positive infinity, which means as k goes to infinity, the branch point will be infinitely far away, which is to say it will be gone. The natural boundary tends to infinity, which means as k goes to infinity, we get our extremely nice behavior. The integrable behavior, just poles. There's still some odds and ends to clean up. I haven't tidied some of the numbers. I need to do the numerics. But finally, I think I have a clear picture of where this integrability comes from in this family, which seems to have no business being integrable. This explains, at least to my satisfaction, and I hope to other people's satisfaction, how you can get this integrable behavior limiting from this very non-integrable series. We got a lot of use out of the part A approximation. In the final problem, I'm going to talk about what happens if it can't help us, but if you'll just bear with me for one moment. I apologize, I've been dealing with this the whole time. My in-house seminar, I didn't fix that, and it became very uncomfortable. All right. So finally, I want to talk about exponential asymptotics using numerical analytic continuation. What happens if I don't even have an analytically continued leading order behavior? Can I get around that? Now, some of this is retreading material I gave in my seminar, but we pushed it a little bit further. So a lot of this was done with John Chapman and Sam Crew. Anything good, that was me. Anything bad, that was Chapman. No, I'm joking. That's not true. So this is actually, I think it's KDV5. No, it's an NLS. Either way, it's a nonlinear wave, singularly perturbed, exponentially small oscillations. First problem you make your grad students do. It's got some poles. They generate a Stokes line. It's got exponentially small oscillations. You churn the handle. You get the oscillations. Everyone's very happy. Being able to do this is very much contingent on knowing where these poles are. Knowing where these poles are depends on knowing what this leading order solution is so that you can analytically continue it. Real life is a little trickier sometimes. So maybe instead of some nice analytic solution, someone gave you a bunch of points. Fixed domain, maybe a bit noisy. Can you recover anything sensible about the oscillations? And the answer is bafflingly yes. Surprisingly robust, but it has to be robust, right? Like, if this technique has any merit, then it has to be robust to the kind of small perturbation and noisy nonsense that we're trying to get around here. So can I start with data. Let's say data, but it could easily be noisy. Like this, can I recover Stokes structure? Does it make sense to recover Stokes structure? Can I figure out what the oscillations are? So what I'm going to do is I'm going to say, well, the first thing you want to do, the most basic numerical analytic continuation, is to approximate the points as a rational function. And the classic rational function approximation is PADE, which we've met already in this talk. You can approximate your function as P of x over Q of x, where they're both polynomials. It'll have singularities. They will generate Stokes lines. Everybody is happy. The polynomials are found in terms of the Taylor coefficients, so all of the coefficients at 0. But this isn't ideal. And the reason it's not ideal is we don't really have all of those derivatives at 0. We have a bunch of points. Now, you can estimate derivatives from a bunch of points. That is kind of what we've been doing in the previous few problems. But for this purpose, it's not really ideal, because applying finite differences at progressively higher order is really going to magnify your numerical error. Really, we want something that's a bit more robust and perhaps a bit more well-designed to the form of data that we're getting. So I'm not saying that the method that I'm about to use is better than PADE. That is wrong. What I'm saying is the method is maybe more designed for the form of data I'm talking about. There's a method called the adaptive Antulis-Anderson method, or AAA. It's become, a lot of people have been using it quite a lot lately, and I decided why not see if it works for our problem. It is a rational approximation method, much the same way. Just by the by, I'm going to write my rational approximations from now on as a sum of simple poles. It just makes the analysis a little bit easier. It's partial fractions. So rather than computing a bunch of derivatives, this method optimizes the coefficients in the rational approximation to best fit the solution over a support set. So it says, well, if I assume all of these are right, then I'll pick my coefficients to do a least squares optimization of the rational function at each of those points. And it has a tolerance, and it increases the number of poles and zeros to make that work. So given some number of poles and zeros, it optimizes the polynomial coefficients. If it beats the tolerance, then it stops, and if it doesn't, it throws in another pole. What this does is comes up with the best least squares approximation on that support set. Like the PADE approximation, it impersonates branch points as an accumulation of poles. And that is actually the point that I want you to really hold in your mind as we go forward here, because this is the thing. This is the interesting thing, the thing that we actually have to overcome. So what I did, and I did this in my previous talk, is I started with the world's simplest linear problem. Epsilon squared u dash dashed plus u is a sum of two square root branch points. AAA should have trouble with this. AAA wants things to be poles. And we're like, you can impersonate a pole as a branch cut, and that's quite hand-wavy. Does that work if we're really looking for exponentially small stuff? So the true behavior, the true leading order solution, is this expression here. It was designed to be very easy to get. And you can calculate the exponentially small behavior asymptotically. Again, it was designed to be relatively easy to compute. The approximated behavior looks like this. The number of poles depends on the tolerance you ask for. So you've got this sum of simple poles. They appear in complex conjugate pairs. So I wrote that there just to remind me of that fact. And you can calculate the exponentially small stuff. Now, there's a few things that should be setting off some alarm bells if you didn't see my talk before. The most important one is this is an exponential multiplied by a 1 on square root epsilon prefactor. This is an exponential multiplied by a 1 on epsilon prefactor. At some sufficiently small epsilon, those two things have to be different, which seems like it breaks everything. But then I decided to try it. The black solid line is the AAA approximated result. The black dots are the true asymptotic behavior, and they are on top of each other. It works incredibly well for this value of epsilon, in fact, quite a lot. And the other thing that's sort of relevant is a lot of the poles are contributing. The individual pole contributions are shown as the blue curves. It's not like there's just one pole that is right and the rest kind of coming along for the ride. You actually need all of the poles. But it seems to work very well, which kind of goes against what we thought would happen. So I plotted the amplitude, the ratio of the amplitude of the approximation versus the so the AAA approximation versus the straightforward exponential asymptotic approximation. We want it to be 1, and for most of it, it is, which is very nice. And as we said, for sufficiently small epsilon, it's going to break down. So now we have an approximation that's good for sufficiently small, it's a small epsilon approximation that breaks down when epsilon gets too small. So like, it's a smallish epsilon approximation. But of course, by increasing the tolerance, you can force that further and further down. We had some explanations as to why this works and why it breaks where it does. If you want to see those, you can go back to my talk from the program. I'm not going to dive into that here. Suffice it to say, there are good reasons why actually this works. And fundamentally, it's because this is a discrete Fourier transform of that, and you can kind of figure out from there how it optimized. Because of Parsifal's theorem, the coefficients will minimize the least squared error in Fourier space, and therefore everything will work okay. So that's quite nice for an easy linear problem. And what I said I would do is have a bit of a bash at nonlinear problems. It will not shock you to know that things are not so nice. So let's write down the easiest nonlinear problem. This thing, the constant just makes things nice, don't worry about it. Mostly the important thing is now I have a u squared. So I have a u squared, and I can get the true leading order, it looks like this, and I can get the exponentially small behavior. One thing I want to point out that is different to the previous one, here, at the very least, the stuff in the exponential was the same, modulo a shift. Here, the stuff in the exponential, and I've expanded around the poles just to make it, the singularities just to make it obvious. Here it's a 4/3 singularity. Here it's a 1/2 singularity. Sorry, that should be a 3/4 singularity. I apologize. Here that's a 1/2 singularity. So even the exponents are wrong. Everything doesn't work. A point that's just worth bringing up is there's this lambda in front. We can calculate the lambda. It's just a value like 7. Here, each different contribution has a different constant sitting in front, so I wrote that it depends on the residue, which it does, because you expect the residue to turn up there, and it'd be a bit weird if it didn't. So I get these two things, and doesn't work so good. So that's nice. It shouldn't work so well. I knew going in that this wasn't going to work. And I knew it wasn't going to work for a very good reason. In this problem, you can just add pole contributions. It's linear, superposition is your friend. You can just add all the contributions together and stuff will work. The sum of the contributions is the overall contribution. Here, it's nonlinear and you do not have superposition anymore. You have to get a bit smarter. So it doesn't work, but we can fix it. Well, let's first understand why it doesn't work. Nonlinear problems don't respect superposition. We can't just add the pole effects. Well, we actually sort of can. Dingle tells us that as long as the poles are relatively well separated, then everything will be fine. The problem is when they aren't. And in fact, the very thing that makes it work in the linear case is the fact that the two closest poles are pretty close together. In fact, closer than epsilon. But that is the very thing that causes the nonlinear problem to break, because you have to think of poles that are very close to each other a little bit differently. Phil Trin and John Chapman did some work on coalescing singularities in the past, and it's actually not wholly dissimilar, although you don't tend to think of them coalescing because they're not moving around. So for instance, if they're very, very close, say here's my first contribution and here's my second contribution, and this delta is much, much smaller than epsilon, then you can just add the residues. The problem is often they won't be quite that close. So I'm not going to show it here, but I did a bunch of numerical experiments and the like, and we were able to demonstrate that this is exactly what's causing the problems. And in fact, if you implement a fix that works like this, then you can recover a good approximation of the behavior. The catch is it's really hard because this is typically not much, much smaller than epsilon. It's typically like ballpark epsilon-ish, which means we have to really think about the distinguished limit. And that bit I haven't cleaned up yet. Because if you know the order of the singularity, there's a sort of obvious easier way. A much easier thing to do, if you know the order of the true singularity, is just apply some conformal map to turn it into a pole, or a double pole, or something that AAA can deal with very well. So for instance, in this problem, because we had square root branches, Just square everything. You'll pick up some nonsense because of the squared. That's not a linear operation. But what this will effectively do is spread out the poles. It will spread out the poles. You're no longer doing the least squared approximation in Fourier space, but you do have the poles well enough separated that you can recover the behavior. It's hard to see, but this is two curves on top of each other. This is accurately, for this one pair, I could show you a graph of the error like I did in the previous one, and it's fine. It's not as good as the linear case. But I find two nonlinear curves sitting on top of each other a little more compelling. This does work. And for a lot of problems, even if you don't know the exact singular behavior, you can at least estimate the order. For instance, KDV, double poles, balancing argument. For many, you can't. So there is one last thing, which is that you can actually think about how the branch point, the poles accumulate in the approximation of the branch cut. So Trefethen has some work on this, where just by looking at the accumulation rate of the poles, you can come up with a good estimate of the singularity strength. And if we can use that to invert, then we're looking pretty good. Doesn't have to be a power. For instance, if it's a log singularity, the smart thing to do is to take a derivative, and so on and so on. The transform inversion method is much easier to implement than dealing with the distinguished limit. And given this is essentially a tool of convenience rather than theoretical depth in some way, maybe the easy to implement thing is the best way to do it. The mathematician in me really wants to get to the bottom of that distinguished limit, and one day I hope to, but it's nice to have a fairly practical method to kick us off. It would be nice to do it properly. A final point that was inspired by a conversation with Gerald Dunn is how robust is this to noise? So what I've done here is approximated the Stokes curves and singularities of Painleve I. Painleve I tree trunqué solution has a square root singularity at 0. Had to be a bit smart here. I squared it and I looked for zeros rather than poles, which you can absolutely do. The algorithm gives you both. And as soon as you do a nonlinear transformation, you have to look for both. It dumped a whole bunch of poles here where I prescribed the data. The color tells you how strong the residue is. The residue here is about 0.01% of the residue of the true singularity pole. So you do a bit of filtering and throw away the small residue terms, and it throws away all of the poles that get dumped there to deal with the noise. It's a nonlinear equation, so the singular equation depends on the initial condition, depends on the leading order, which we have an approximation for, but it predicts the Stokes sectors perfectly, as good as, because aside from funny business near the singularity, the global behavior is spot on. So if you get it right here, you're definitely going to get it right everywhere else. So it's quite strong. That is all I had to say. I have 3 minutes left, so I'm going to get you out of here to lunch on time. These problems weren't picked at random. Each of these problems attacks something which I've been thinking about for a very long time. Discretization, transasymptotics, analytic continuation. These are all ideas that I think if we get a real handle on how they merge with exponential asymptotics, we can do some really powerful things. Integrability, maybe there's easier ways to get the Stokes constants. Transasymptotics, Stokes phenomenon gives you the skeleton, transasymptotics gives you the meat and muscle. Like those two things together tell you what a function does. These are all things that I wanted to understand a lot better when I turned up here, and I think I did. So yeah, it was worth missing out on summer. Hopefully I'll get one next year. Thank you very much for listening. I really appreciate your time.
Thanks, Chris. So, questions, comments?
So for your discrete singular perturbed problems, do you have examples where the h and the epsilon, there's a distinguished limit for that?
Well, there wasn't an epsilon in the KDV one that I did, but the problem Aaron Mostyn-Duggan did during the second workshop, my PhD student, had a natural epsilon in the equation, which meant it was the natural choice for h. The interesting thing about the KDV one is that it doesn't have a natural epsilon, so the only small parameter is the discretization. this is why it's essentially a fake boundary layer rather than a true
No,
one.
I thought there was a bit where you said you wanted to do the...
Sorry, can you speak up?
I thought there was a bit where you said you wanted to do the discrete problem, but with an epsilon, with a further...
No, that wasn't a discrete problem. I wanted to do this continuous problem, which was the first truncation of the discrete problem. So you can think of the epsilon as essentially playing the same role as the h. But that's a good question, because that comes back to this in the sense that when there's a true epsilon in the equation, the boundary layer in the Borel plane is important and you need to consider it. When there's not, then even though you can do it that way, it doesn't actually have a boundary layer type effect. So that is something that is really worth thinking about. And I don't want to say that every discretization induces this sort of behavior. In fact, one of the reasons we looked at the NLS is the kind of naive finite difference discretization does not induce oscillations. They all decay away. Like, it creates something. It's still singly perturbed, but they all disappear. Whereas when you do the epsilon, you do the fourth order perturbed one, you get these oscillations. Another thing that we want to think about is symplectic discretizations, a discretization that respects the integrability of an original system. Does that get this weird behavior, or is it nice all the way up? So this is something that we want to think about going forward as well, which is sort of combining the integrability and discretization.
And just a quick question on the AAA stuff.
Yep.
Do you ever use how the AR is actually generated, this least squares thing in the analysis?
Do I ever, sorry, I missed how that.
Do you ever use any aspect of how the AR is actually generated?
Not in the analysis. So it's generated as part of the least squares approximation, and mostly I don't touch that. That's nice and built in. However, as we go into nonlinear problems, this is really good for linear problems because of Parsifal's theorem, which means for linear problems, you know it's going to work. For nonlinear problems, that's actually worth revisiting. Is this the right thing to optimize? Is least squares the correct optimization, or do we need to get a bit creative? To which I don't know the answer, but it's worth considering.
Thanks, Chris.
Anybody else?
I seem to recall a recent preprint on Berger's equation in the complex plane where someone did the anti-Stokes line by matched asymptotics. Have you tried comparing that with your transasymptotic answer?
Not yet, because we haven't fully gotten the answer. Also, was that not our preprint, just to check? Okay, just making sure. Yes, we plan to. And that has the first correction. But of course, because the transasymptotic method, we can get A1 and A2 and so on, we can easily get all the rest of the corrections to it and hopefully improve on what we got from that analysis. Which is not to say that couldn't be done in other ways, of course, but it would be nice to validate it that way, and we intend to. It would be weird if they didn't agree.
Yes. Maybe I can ask a question. In that last example, do you think, therefore, AAA could be used as a noise filter?
That is too big a claim for me to make, I think. You could see a way forward in that line, but I would have to think of it a lot more before I could commit to an affirmative answer. In some sense, by throwing away the very small residue terms, you are smoothing. So the question is, could it be any more effective than a pretty standard low-pass filter? And I don't know that that's true. It strikes me as unlikely.
Okay.
But I don't know.
It violates the no free lunch theorem, right?
I beg pardon?
It violates the no free lunch theorem. Since we're going
there's
to
no free lunches here.
Since we're going to a free lunch now. All right, let's thank Chris again.
Thank you.